Hi, I am Radoshik Paul. I have done M.Tech from IIT Patna and my B.Sc and M.Sc from Calcutta University. Today I will tell you about this topic, that is partition function. It is very important for CSIR NET physics and GATE physics exam and also for M.Sc physics exam too. So what is partition function? It is basically a function that describes how various particles are distributed in various energy levels in a system. Okay, so it basically correlates, partition function basically correlates the macroscopic properties of a system or macrostates of a system to its corresponding microstates. Okay, so what are the microstates? First, microstates. What are the macrostates and what are the microstates of a system? So when we consider the molecules of a system as a whole, means when we consider the ensemble average of molecules of a system, then we are talking about the macrostate of the system, and the parameters are here. Macroscopic parameters are, like example is volume, temperature, means that parameters which we can directly measure from the system. Those are the macroscopic parameters of the system. And for microstate, when we consider the individual molecules of the system, then we are dealing with the microstate of the system, and the parameters are like internal energy U, chemical potential mu. These are the parameters that related to the behavior of single atoms, single molecules of the system. So these are the microstates of the system. Okay, so now let us come to the classification of partition function. Okay. Partition function is basically of two types. One is discrete type or quantum nature, and another is continuous type or classical nature. So for the discrete type, the expression of the partition function is J equals to summation over Gi e to the power minus beta ei. And for the continuous type, the expression of the partition function is Z equals to 1 by h to the power f into the power minus beta h dfp dfq, where f is the total degrees of freedom. Means if it is a if each particle has 3 degrees of freedom, and if there are if each particles have 3 degrees of freedom, and if there are total n molecules, then total degrees of freedom f will be 3n. And that is the f equals to total number of degrees of freedom of all the particles of the system. Okay, h is the Hamiltonian, and dfp dfq is the elemental volume in the phase space. And for the discrete type, the gi is the degeneracy of the state. Okay. Now let's come to the derivation of the discrete partition function, that is this expression. Okay. Let two states, there are two states with a partition between them. One state is energy epsi and particle number of particles n1, and another state have energy epsa2 and the number of particles n2, and there is a partition between them. This total is a system, whole system, two states epsa1 n1, epsa2 n2, and the temperature of the whole system is there is temperature equilibrium. Okay. Now if we remove the partition, then this there are particles, so this become a whole system with number of particles n equals to n1 plus n2, and let the energy becomes E, equilibrium energy E. Okay. Now if we take a single molecule from there, or a single particle from there, then what will be the probability that that particular particle will be from this n1 number of particles, or what will be the probability that that particular particle will be from this n2 number of particles. So let probability p1 is the particle from energy epsa1, and p2 will be the probability that the particle from energy epsa2. Okay. And also assume that the number of degeneracy in this state, one state is g1, and number of probability in epsa2 state is g2. Number of degeneracy in epsa2 state is g2. What is degeneracy? Degeneracy means, let us assume that the energy, there are three states which have energy epsa1, three states, and there are five states with energy epsa2. Means these three states all have energy epsa1. So here for this epsa1 states, the degeneracy g1 equals to 3, and there are five states with energy epsa2. Five states each have energy epsa2. For epsa2 states, the energy g2 is 5. And how the number of particles will be distributed in three states? Like if the first state has one number of particle, the second state has 3 number of particle, and there are total n1 number of particles, so these states will have total number of particle n1 minus 4. That is how the particles will be distributed in these energy states. And similarly the particles will distribute in epsa2 states also. So let us assume that for the first state 1, the particles, the degeneracy is g1, and for state 2 the degeneracy is g2. Now p1 is to probability of the particle from the energy epsa1, and p2 is the probability of particle from energy epsa2. This is the probability. Okay. So P1 will be proportional to e to the power minus Boltzmann factor of that state, beta epsilon, and also will be proportional to the partition function g1. So P1 will be proportional to g1 e to the power minus beta epsilon. Similarly, P2 will be proportional to g2 e to the power minus beta epsilon. Okay, let's erase this. We can write that P1 equals to A into e to the power into g1 e to the power minus beta epsilon, and p2 you can also write a g2 e to the power minus beta epsilon 2. Okay, so yes, where a is a constant. Now when you remove the partition, the two states become a whole system. So, and we know that for a whole system total probability p equals to 1. So, and total probability will be the summation of the state 1 and state 2. So p1 plus pp equals to will be p1 plus p2. So p1 plus p2 equals to 1. Or if we put the values, then it will become a into g1 into the power minus beta e1 plus g2 e to the power minus beta e2 equals to 1, or a equals to 1 divided by g1 e to the power minus beta e1 plus g2 e to the power minus beta e2. Okay, so here p from this equation, p1 will be g1 e to the power minus beta e1, and if we put the value of a, it will become g1 e to the power minus beta e1 plus g2 e to the power minus beta e2. That is p1 will be equals to g1 e to the power minus beta e1 divided by this term g1 e to the power minus beta 1 plus g2 e to the power minus, this term is written is known as a partition function z. Okay, so z for discrete system or quantum system, partition z is g summation over I gi e to the power minus beta epsilon, where gi is the degeneracy of ith state and ei is the degeneracy energy of the ith state. Okay, now let's come to the properties of the partition function. Properties. Property 1. If a distinguishable, if a system has n number of distinguishable particles, then overall partition function Zn equals to z1 to the power n, will be z1 to the power n. If a system has n number of indistinguishable particles, then overall partition function Zn will be, here the number of particles, the partition function value will be less from the distinguishable one, that is indistinguishable particles. So the particles are indistinguishable means the way the particles can be arranged, the number of ways the particles can be arranged will be less than the distinguishable case. So here also the partition function will also be less from the distinguishable case. For indistinguishable case, the number of arrangement will be less from the distinguishable case. Also the partition function will be less from the distinguishable case. This is z1 to the power n by n factorial. Let's come to the property number 3. If I and J are two different independent non-interacting systems, then their overall partition function Zij equals to will be product of their individual partition function. Okay, so let's prove this. Let the system I has degeneracy Gi equals to 1, means it is non-degenerate. System J has degeneracy Gj equals to 1, it is also non-degenerate. Okay, now the probability of Py will be e to the power minus beta Ei by Zi. Probability of Pj will be e to the power minus beta Ej by Zj. Now if we combine these two systems, then the whole probability will be Pij equals to e to the power minus beta epsa. Epsa is the energy of the combination of I and J, and the combined partition from Zij. Now the energy of the combination will be summation of the individual energy, means Ei plus Ej. So, and now these two systems are independent. So means these two systems probability, the whole probability Pij will be, as these two are independent set of events, so this probability of these two systems will be multiplied, means these two are different events, so their probability will be multiplied. So Pij equals to e to the power minus beta Ei plus Ej divided by Zij equals to Pi, means e to the power minus beta Ei by Zi into Pj, means e to the power minus beta Ej by Zj. Okay, so from here we get e to the power minus beta Ei plus Ej by Zij e to the power minus beta Ei plus Ej Zi into Zj. So this will be cancel out and we will get Zij equals to Zi into Zj. Means here I and J are two independent non-interacting systems, and if we consider their overall partition function, then the overall partition function will be multiplication of their individual partition function. So let's now solve a problem regarding partition function. The problem is a system consists of three independent particles localized in space. Each have energy either 0 or E, and then the system is kept in equilibrium with a heat bath or temperature T. So then calculate its partition function. So this particular problem can be solved using two methods, method 1 and method 2. So let's first discuss the method 1. That is, first we will calculate the single particle partition function, then we will calculate the three particle partition function. So method 1 is, first we calculate the single particle partition function, that is Z1. Here 0 energy set E are degenerate, means they are non-degenerate, means their degeneracy is 1. So 1 into e to the power minus 0 into beta into e to the power minus beta into 0 plus 1 into e to the power minus beta into E. Here beta equals to 1 by kT, as the system is in thermal equilibrium at temperature T. So this will become 1 into e to the power 0, means 1 plus 1 into e to the power minus beta E. Okay, and now the n particle partition function will be Z1 to the power n, because here the particles are independent. so they are distinguishable. So the n particle partition function will be z1 to the power n. So 3 particle partition function will be z3 equals to z1 to the power 3, means 1 plus e to the power minus beta e whole to the power 3, means 1 a plus b whole cube, 1 cube plus 3 into 1 square into b plus 3 into 1 into b square plus b cube power minus 3 beta e, that is 1 plus 3 e to the power minus beta e plus 3 e to the power minus 2 beta e plus e to the power minus 3 beta e. That will be the answer of the partition function. So this is method 1. So let's now discuss method 2. Okay. So first write the energy states. This is 0 energy states and this is energy state E. Okay. And let the particle be A, B and C. So first we divide, and here it is, in this column the energy is 0, in this column the energy is E, in this column this is total energy. Okay. And here it is degeneracy. In this column it is degeneracy. First we will put 0, we will put all the particles A, B and C, 3 particles in the 0 energy state, and we will put no particle in the E energy state. So here A, B, C. So A, B, C, all the 3 particles A, B, C are in energy state 0. So total energy will be 0 because all the particles are in 0th energy state. No particle is in eth energy state. So total energy will be 0 here. And this is only one combination. No other combination is possible for this. So their degeneracy will be 1. Okay. Now we will, in the next step, we will distribute the particles in such a way that 2 particles will be in 0th energy state and 1 particle will be E energy state. So here, so this process, this step can be viewed in 3 different ways. Like first, A and B will be in 0 energy state and C will be Eth energy state. Next, B and C will be 0th energy states and A will be E energy states. A, B, B. And in the third one, A and C will be 0th energy state and B will be E energy states. So here, when 2 particles are in 0th energy state, so their total energy will be 0. And when 1 particle in Eth energy state, so their energy will be E. So here for the first case, 2 particle AB is in 0, C is in E, so total energy will be E. BC is in 0, A in E, total energy will be E. AC is in 0, B in E, total energy will be E. This is one case. So here 3 different distribution are possible. So the energy will be 3. For all of these 3 cases, the energy is E. So degeneracy is 3. In the next, we will arrange 1 particle in 0th energy states and 2 particle in Eth energy states. The reverse of this, okay? Reverse of this. So here 1 particle A is in 0, B and C is in E. 1 particle B is in 0, A and C is in E. 1 particle C is in 0, A and B is in E. Here, when 1 particle is in 0th energy state, 2 particles are in Eth energy state, so their total energy will be 2E, because this contribution of this particle to the energy is 0. So here for first case, the energy will be 2E. For this distribution, the energy also will be 2E. For this distribution, energy also will be 2E. Here also, for 2E energy states, 3 different combinations are possible. So here degeneracy will also be 3. And in the next case, we will distribute the particles in such a way that there will be no particle in zeroth energy states, and all the three particles will be eth energy states. So here no particle is in this energy states, and all A, B, C are in eth energy states. This is the reverse of first case. Okay, first and fourth are opposite, 2 and 3 are opposite. Okay, so here three particles are in eth energy state, so the total energy will be 3e. Here with 3 energy only one combination is possible, so degeneracy will be 1. So yeah, so if we calculate the partition function like this formula, summation over I gi e to the power minus beta ei, and if we calculate the partition function from this table, so it will become like, for the first case degeneracy is 1, energy is 0, so 1 into e to the power minus beta into 0. Okay, for the second case degeneracy is 3, energy is e to the power minus beta e. For the third case degeneracy is 3, beta is 2e, e to the power minus energy is 2e minus 2 beta e, plus for the fourth case degeneracy is 1, energy is 3, so e to the power minus 3 beta e. So this will come 1 plus 3 e to the power minus beta e plus 3 e to the power minus 2 beta e plus e to the power minus 3 beta e. So we can see that using method 1 or method 2 we are getting the same result in both cases. Means the problem can be solved in either of with method 1 or with method 2. Both are good methods. Okay, thank you.